anywhere.
Oh, okay.
I see it now.
Okay, sorry about this. Thank you. Yes, I didn't do this correctly. Okay, sorry about this. So for anybody who is joining us, now, thank you, Mehdi, for pointing it out. I just started a lecture on recursive algorithms, and we are starting on slide 2, an example of the first example of a recursive algorithm. It's a computing exponentiation. Okay. Sorry about starting the recording late. Okay, so so I'm trying to. So here is the recursive. Okay, what am I trying to compute? Exponentiation. A is the base, n is the natural exponent. So here is the recursive code for computing that. It has two parts: a base and recursive. The base case takes naturally the smallest integer for which is in the domain, right? I want to compute this function. My domain is pairs, where A is anything really, right? Any real, but n is non-negative, so integer, so starting at 0. So my base case is n equals 0. Notice A is not even considered, it's essentially considered constant here. The only variable on which recursion goes here is n. Okay, so I treat these inputs unequally. Okay, but it works. Okay, so the base case n equals 0. And how do I how can I compute a to the 0 by hand? Well, it's easy. In fact, it's simply equal to 1, no matter what a is. Right, so you know that a to the 0 for any a is 1. So that's what we return. In any other case, right, for n greater than 0, so n is some now positive integer, we will do it recursively. We'll compute the power with one less exponent, right? The exponent is one smaller, and we will return this as an answer, right? So this is here a recursive call, because how does this algorithm run? Well, if n is 0, then it just returns it here, right? But if n is non-zero, then it will jump to this clause, and it will call itself on n decremented by 1. So if you say take n equal 10, this will generate a call to power a with exponent 9. So it will jump here with a modified variable. So now n will be 9. Again, it will skip the base case, and it will call here with n equal 8, and so forth, right? So in case this is the first time you see it, let me go to the document camera. Hold on. Aha, yes, I have it here. Good. Okay, so I have this little piece of code, right? Power an is if in the base case where n is 0, I return 1. In the recursive case, first I make a recursive call to the power algorithm with decremented exponent, and I take the result, whatever this recursive call returns, and multiply by a. So just notice that also I could say this slightly faster by rewriting this code like this. In the base case, it's the same as above, and in the recursive case, I directly return a product of a, which is this, and whatever the recursive call returned, which was called p here. I just don't use this variable. Okay, so let's look at how this behaves. So let's say I'm calling power a, and really it doesn't matter what a is, 5, right? So in this call, n is 5. So if n is 0, then I actually am not interested because n is not 0, so I can forget this part. And I see that, okay, else return a times power of a and n minus 1, which is 4. So this will generate a call, recursive call to power a4, right? The code is the same code. So if n is 0, then, but I'm again not interested because n is not 0. So I jump to the else clause that says return a times power a3. That generates a recursive call that goes its power a3 if n0 I ignore, else return, so this is a product, sorry, a times, then return a times power a2, okay, and this, so here n is 2, if n0 again I ignore, else return a times power a1, okay, so that will make the call on a1. If n equals 0, I don't care, else return a times power a0, okay, and this is great, okay, not the best, sorry about that. Okay, hold on a second, I have a solution. Sorry, just dancing around a little bit. Okay, so I ignored this previous version of the same algorithm and just use it here. Okay, now we are good, right? So in this call, n equals 0. So this call says if n equals 0, and I finally hit the base case, right? Which is, and what was it? Then return 1. Okay. So in this code, I can actually ignore the recursive call because I'm not going to go there. So this returns 1. So this value is 1. So this value will be a times 1, which is a, right? So it returns a. So therefore this value is a. So therefore this value will become a times a square. And we return, therefore, because it says return, right, to this call, it's going to return a square. And you can notice that, oh, so that's good, because power a2 is a square. That's, I'm in a good shape. So this thing is a times a square, which is a cube, and I return it. Okay, so it's the same sequence, right? This will become a4. I return it. And therefore this is a4, and therefore this is a times a4, which is a5, and that's great, right? Because I return, therefore this is going to return to whoever calls this. We are going to return a to the 5th, and this person should be happy, right? Any questions on this? Okay. Could you repeat? Okay. Maybe somebody tried to ask a question, maybe not. Okay. So all right. So you can see how you can follow a recursive algorithm, right? To sort of see how it works, and that in this case it was a fairly simple algorithm, and it did seem to create correct answers, right? For Okay, for this case, at least for the cases that we looked at. So how about a general claim, right? I want to claim that this power algorithm will always return the correct value, right? So it wasn't a coincidence that it worked correctly for n equals 0, n equals 1, 2, 3, 4, 5. I stopped there. And how would I argue such a claim? Well, you can guess that I would do this by induction. Induction on n, right? Because the whole power algorithm, right, defined what it will do for n variable in terms of what it would do at n minus 1. So that seems similar to the way we did recursive sequences, right? And it seemed like induction was a useful tool about proving properties of recursively defined sequences. There is no really difference between this, what you are just this code, and a recursively defined sequence, right? So perhaps this would be a good, as good a moment as any to point that out. So let's, okay, so what was the code again? Okay, please focus camera. Doesn't want to focus for some reason. How about I press this button? It performs some, okay, good, it focuses itself. Excellent. So here was the code. Power an is defined if n is 0, then return 1, else return a times power a n minus 1, right? That was it. All of it in its entirety, right? So here is, I claim a completely equivalent thing. Let's define an sequence, define a sequence an for n, and by the way, this was supposed to work for all n greater or equal to 0, right? And I will likewise define a sequence starting at 0 as follows. A0 is 1, an is a times a n minus 1 for all n greater or equal to 1, right? This is just a recurrence relation for this sequence, and this is a recursive algorithm for power algorithm, right? And there's basically, they're one-to-one to each other. There's like, it's the same. It's the same thing, exactly. Okay. So what you're seeing today is this, and it's just what you already know, but in disguise, right? And a pretty thin disguise also, right? Okay, so let me go back to these slides then. Okay, so again, how would we prove? So I want to prove that this returns correct value, and oh, one more parallel, right? So look, what do you know how to prove about sequences? So I'm going to have a claim like this: for all n greater or equal to 0, closed form for this sequence an is that an is equal to a to the nth power. Oh god, let's screw that up. A to the nth power, right? A very natural claim, because what is this sequence really? It's a geometric sequence, right? It's a geometric sequence that has factor a and initial point 1. So it's obviously a geometric sequence, right? Explicitly. So we know that the geometric sequence has this closed formula, right? And already for this homework, I could ask you, how would you prove this? Obviously by induction, right? And you're already familiar with this version of these proofs because this is identical to this. And the claim that this algorithm returns this value is identical to the claim that the closed form for expression for this sequence element is this one. There is like no difference between these claims, right? So it's no surprise that it's also the same proof, because you're really proving the same exact thing, right? It's just slightly disguised. All right. So, but let's do it explicitly. Prove this thing for this for this claim now rendered as a claim about a recursive algorithm. So by induction on n. Okay. Well, so the base case, the first one, is n0. So let's look at what power of a0 does. Well, it obviously hits the base case and just returns a 1. And that's a correct thing, right? Because 1 is indeed a to the 0 regardless of a. Okay, so far so good. Let's move to the inductive step. So what we want to show is that for any integer k greater or equal to 0, and you can call it n, and you can also shift it. I mean, it doesn't matter. They're all equivalent. But be careful when you're doing these shifts, because if you shift this, then you have to also shift these things. All right. So maybe that's, yes, so like a student said at the beginning, you have some freedom in how you exactly state these things. So for all integers k greater or equal to 0, if the power algorithm works correctly, returns the correct value at point k, then I want to claim that it will return the correct value at an increment, k increment, right? At 1 larger, at k plus 1. And that would be, so what's my predicate that I'm proving about n? The predicate is this. This is the predicate on n, right? The predicate on n, what happened to a? The predicate on n is for all a, power an returns a to the n, right? So this is the predicate on n, and a is just a free, I mean, there is really a hidden for all a here. Because indeed, like everything we say works for any a, right? So we don't repeat it. Okay, so so this says if the predicate holds at k, then that same predicate holds at k plus 1, right? Because this is the predicate we're proving. Okay, so how do you prove this thing? Well, this is your goal, right? Your inductive goal. So you have to see, okay, what does power a k plus 1 algorithm do? Okay, and basically you just read it off from the code. So in this case, I mean, the only thing is that you have to make sure that you don't get lost in variables, right? So that you don't mess them up. So in this call, variable n is equal to k plus 1, right? So the code really, let's just instantiate it with n equal to k plus 1 and see what happens, right? So this line would be if k plus 1 is 0, and of course, if k is greater or equal to 0, then this will never happen. So I don't even have to look. And then else clause is that I'm going to compute p as a power of a n minus 1. But n is k plus 1, so n minus 1 is k. And then whatever this thing returns, I'm going to return that thing multiplied by a. Okay, so good. So I know what power of a k plus 1 will do. It will return a times power ak. Okay, so then, right, so this is what I just read, that this is what power of ak plus 1 will do. I read it from here. Now, you kick in the inductive hypothesis, right? That the previous call, this recursive call, returns the correct value, right? Because luckily, this is with a smaller element, so you can use the inductive hypothesis. So you do. And then it's immediate, because if power a k plus 1 returns a times p, and p is a to the k, then I rewrite this in this way. And clearly, this just increments into the exponent like this, right? It's just one more multiplication times a. Okay. So that's the end of the proof. And you could see that it's identical to the claim about recursively defined geometric sequence, because that's exactly what this is, that the closed formula for it is this, for a geometric sequence that starts at 1 and multiplied by a at every step. Okay. So, okay, but you know, you could also prove something else. Not only, so this is what we have proved on the previous slide, is I would call algorithm correctness, right? That it returns the correct value. How about the running time? How about like measuring how many steps this algorithm costs me? Okay, so a simple claim is that the algorithm at exponent n is going to perform n multiplications, right? And if you just stare at the way that the algorithm works, it's kind of obvious, right? Because yes, at every time I call it with the parameter n, I'm going to have a multiplication and a recursive call. And the recursive call is with one less exponent. So every time I decrement an exponent, it costs me one multiplication. And so how many multiplications I will do? As many as the number of decrements until I hit the base case. Well, the number of the decrements is obviously n, right? It takes you n decrements to get from n to 0. Okay, so this is how the recursion induction would, but formally we prove it by, I mean, this, what I just described, is an inductive argument, but it's just informally phrased, right? But a formal one would start with a base case, and so and see that, okay, this predicate is true for n equals 0. Indeed, power a0 performs 0 multiplications because it hits the base case and performs no arithmetic operations whatsoever. Okay, and now in the inductive step, for k greater or equal to 0, well, okay, so that's what we will be proving, that if the predicate is correct for k, for n equal k, so therefore if this is true, then the same predicate holds for n equal k plus 1. In other words, we want to argue that this is true. Okay, so let's remember again what this algorithm really did, right? If we want to argue that this guy here, power of a k plus 1, performs k plus 1 multiplications, then let's see what it does. Okay, and so it will skip the base case, right? Because k is greater or equal to 0, so this is not true, and it will just hit the recursive case. But look, by the inductive hypothesis, so how many multiplications am I doing into recursive case? Where I'm doing 1 here, and I'm doing however many are done servicing this call. But that's the inductive hypothesis, that servicing this call costs you k multiplications. So therefore, the total number of multiplications you're doing is k here by inductive hypothesis, and one more. So obviously it's k plus 1. End of proof. Okay. If you have a question, you can pipe in. Okay. All right. So let's go on with another example. So to do this other example, I want to just refresh some exponential laws. So these are two laws. If I take a base to x and base to y, that's the same multiplied. That's the same as base to x plus y. So exponents get added if I multiply, right? So if this is, 10 to the 2 to 10 to the 2 is 100 times 100 is 10,000, and that's the same as 10 to 2 plus 2, 10 to the 4th, right? And if I instead of exponentiating sort of sequentially like this, I exponentiate like this. I take a base to some exponent and then take a result to another exponent. Well, that's like taking the original base to the product of the two. Okay. Well, it would be way better if I had a way to look at the chat. Oh, and I do. I actually can look at the chat. Okay, so everyone, please type in with an answer here. Okay, so everybody runs for the C, which is correct, right? Okay, so yes, indeed, this is correct, right? Because k plus 1, I use this law. K plus 1 multiplied by 3 is k plus 1 times 3. That's 3k plus 3 ones, which is 3k plus 3, right? Okay, let's do another one. 4 times 2 to the k, right? So what now? Which of these options should work? Yes, and people say correctly, right? It's this one, right? Because this is 2 to the 2, and now I use this law. So it's 2 to the 2 plus k, which is here. Okay, so far so good. So let's use it for fast recursive exponentiation. It's the fast recursive exponentiation it should get us the same. I mean, my aim is to compute the same thing on the same inputs, any base and non-negative integer exponent. But I will do this faster by using the following algorithm. If I hit the base case, n equals 0, I return the correct value as before. But my recursive step is modified. First of all, I slash n by 2. So rather than look at n minus 1, I look at n divided by 2. And because I have to do integer division, I do n div 2. And again, what is the n div 2? If n is even, then this is simply n divided by 2. And if it's odd, then it's n divided by 2 floor. So it's the floor of n divided by 2, right? So it's as if you removed 1 from n and then divided by 2 for odd. So I jump from n to element d, which is roughly twice smaller, exactly twice smaller in case of even, and roughly and even slightly smaller in case of odd. And I run recursively the FastPower algorithm on that exponent. So I take a to the d here. If this algorithm works correctly, then this thing should return to me a to the d. But but from a to the d, which is a to the n over 2, I can compute a to the n. If n is even, so a to the d is indeed a to the n over 2 exactly, then I take p square from that, because squaring that is going to take n over 2 in the exponent times 2 and get me a to the n. And in the odd case, I do a little error correction here that accounts for the fact that this is not exactly a over a to the n over 2. So intuitively, that's how it works. Let's verify it that this algorithm works correctly. And you know, I guess perhaps it's not such a bad idea to do the, oh, I have to do this, hold on a second, to just do it on paper, right? So FastPower a to the n was if n is 0, then return 1, same as before. And else, compute d as the floor of n over 2. Okay, so that is a diff2 operation. And then compute p, which is FastPower a to the d. And then if n even, return p square, and else, so if n is odd, return a times p square. Okay, that's my algorithm. So let's look at some case. How about we do the same one as before? Although, you know what, it's not gonna be fast enough. So let's do it for FP10. Okay, so here n is 10. So d is going to be a floor of n divided by 2, which is 5, right? So this is going to generate a call that p is fp of a5. Okay, so what did fp of a5? And now in this call, n is 5. So d is 5 to floor. So that's 2, right? So here I will have a call where p is fp of a2. Okay, so this is a recursive call. You know, I'm making inconsistent notations. So so this is the frame of this call, and this is the now I'm looking at this. So here I'm looking at what this did. Here I'm looking what this did, and now I will look what this is doing. So here n equal 2, so I'm ignoring the base case. And I compute d, which is 2 over 2 floor, which is 1. So here p will be fp a1, and this is going to call now the FastPower algorithm with n equal 1. So d is going to be floor of 1 divided by 2 floor, which is 1/2, and I take a floor, so that's 0. So here p is fp of a of 0, and this I don't have to do, right, because this is n equals 0, so it will return 1 because I finally hit the base case. So this will be 1. And let's look how this clause finalizes, right? The clause says, okay, p was 1, and now it looked if n is even, no. So I'm here processing this code in here with this variable n equal 1. So I am in the even n clause. So I return a times p square, but p was 1, right? So this is n times 1 square. So this is just a. So this will return a. And so far, so good, because a to the first is indeed a. Okay. So how will this clause now continue? So I'm in this code. Now I returned p is 2, p is a, and I'm processing this. N is 2. So I'm hitting this clause. So I returned p square. So return p square, which is a square. Okay. So this will return a square here. And I mean, just for right, so this is the odd n case, and this was the even n case. And now I'm in here, I'm in this call. I was calling with exponent 5. I got a2, which is indeed a square. So this was processed correctly. And I'm in this algorithm with n equal 5. So I'm here. So I'm hitting the odd clause. So n odd. So therefore, n odd. So I return a times whatever p was squared, but p was a square. So this is a times a squared. So square. Okay. So this becomes. I see that my handwriting is too small, perhaps, for this to be legible. But this says this, right? And this is a to sequential exponentiation. So it's 2 times 2, so it's a to the 4th. And now I'm adding. This is a to 1 and a to 4th, so this is a to the 5th. And that's great, because this will therefore return a to the 5th, which is what you expect. And now I can finalize this clause. This will be right, a to the 5th. And where am I in this code? I returned p. It was a to the 5th, and I'm processing here, and my n is even. So this is the n even clause, and I return what? I return p square, but p is a to the 5th. So this is a to the 5th square, and this multiplication of the exponent, so it's n to the 10, a to the 10, right? So, and I return a to the 10. Okay. Questions on that? All right. Okay, so maybe I go too exhaustively over this, but let's look at proving that this works simply for any n, right? So a recursive, sorry, here is this code again, written concisely. You divide, you run the FastPower on the division of n divided by 2, and then you return basically p square, corrected in case of n was odd. So our theorem is that this was no coincidence. It really works for any n. And now let's try to prove it by induction. And actually, we'll prove it by strong induction. And so let's look. So how would the structure of the strong inductive argument? Well, there is a base case, right, and 0, and that's the same as before. It obviously works for the base case. Now, what are we proving? What are we proving in the inductive step? We're proving that for any k, if the FastPower algorithm returns the correct value at any argument j in this range, so between j0 to k, then FastPower algorithm will return the correct value at k plus 1. So another way of reading this is like this. I'm arguing that FastPower at a with parameter k plus 1 returns the correct value if FastPower returns correct value for all integers smaller than k plus 1. That's what this says. It says that FastPower worked for all integers smaller than this. And that's what you need in this inductive proof. And now you're going to say, okay, let's maybe it might be obvious for some of you, but why not a standard induction? Okay, so here, why not, right? Let's try to do it for standard induction, right? So the base case is the same. Inductive step. So let's say that what do you have to show in standard induction step? Well, that if the algorithm works correctly at some point, then it will work correctly for the next point. Okay, so let's try to do this, and then you will see that it doesn't work, right? Because, so how can we argue what this does? Okay, some claim about FP executed with k plus 1. Well, we have the code. So we have to instantiate the code with n equal k plus 1 and just see what it does, right? And hopefully, we will, by inductive hypothesis, will see that whatever this does is correct, has to be correct. Okay, so let's see. It's not going to hit the base case, right? Because k plus 1 is positive. So it will compute this division, k plus 1 div 2, and then it will run recursively fp on this division. And that's the problem, because if you knew that this call returns correct value, then you could use it, because everything else here is some arithmetic function of whatever this returns, right? Nothing else is used. Whatever this p is, it's some closed formula, namely this one, hopefully. Hopefully it's a to the d, right? If you knew that, then p, you could replace p as a to the d. And then everything else in this code is in terms of p and a, right? So hopefully this is correctly done, right? But can you use the fact, can you assume that this algorithm works correctly on D? And basically not, because this is your only inductive hypothesis, right? So the problem is right here, that this D is going to be way smaller than K, right? So for example, if I'm calling it at K plus 1, 10, which corresponds to K9, my D is not 9, but 5. That's the beauty of the fast, right, exponentiation, that it skips. It goes to the base case 0 in a much faster way than going 1 by 1 by 1 by 1. So simply speaking, FastPower at 10 is going to call FastPower at 5. So in order to argue anything about correctness or speed or what have you of this call, you need to, the only thing you could possibly use is some correctness or speed or whatever of this call. And if somebody gave you that FP works correctly at 9, it's like, well, that's great, but I cannot use it. It's irrelevant, because FP at 10 just skips and does not call FP of 9 ever. Yeah. So it does, however, call FP of 5, and look, it's clear that no matter what n is, the recursive call here is going to run on something smaller, right? So d is always smaller than n, right? So in higher integers, if you divide it by 2 and floor, then of course you're going to get something smaller than n. The only thing you have to convince yourself that it works for like small guys, right? But it does. From 2, if you divide it, you go to 1, and from 1, if you divide it, it's 1/2 floored, so it's a 0. So it's always, d is strictly smaller than n. So strong induction will be fine, because at this point you hit some, and you don't know exactly which, I mean, you do, but it's some integer that is smaller than n. And so the strong inductive form, right, which is this one, I want to argue that that the algorithm is correct at k plus 1 based on assumptions that it's correct on all smaller values. And this will get me out of this quandary, right? Because, so let's just do it case by case, because I have a split here between handling even and odd cases. I will also argue this for even and odd, but actually it's more convenient, at least for me, to consider k plus 1 even first. So if k plus 1 is even, then well, k plus 1 is 2 times some integer. And when you instantiate this code for n equal k plus 1, then this D is k plus 1 div 2. And if k plus 1 was twice something, then this thing will just get you that something back. So in this case, okay, so that's what D is, right? And if you call P at, so P is the recursive call, which is this. And now it's processed by this if then, right? So I have to look whether k plus 1 is even or odd. It's even, so I can ignore the odd place. And I know that this thing will return p square, right? So, okay, so now by inductive hypothesis, m here is in this range, right? It's half k minus 1. So it's smaller than k. I mean, it's at least, it's you know, it's in this range. It's non-negative, right? The division cannot get you to a negative number. And it's also smaller than what you start with. So by inductive hypothesis, you can kick in the assumptions that the FP algorithm works correctly for all places smaller than k plus 1, right? So this call is going to return a to the m, and now it will be processed correctly, because if I take the a to the m and square it, what do I get? Which is what I do here, right? P squared, and P is a to the m by inductive hypothesis. So I take a to the m and square it, that's a to 2m, right? Because I multiplied these exponents, and 2m was k plus 1, so I'm correct. Okay, and the odd case, okay, well, let's test that everybody is woken up by seeing yes, right, good, yes, okay, yes, it is this value, and why is that? So let's look at this, right? So k plus 1 div 2, it's 2m plus 1 div 2, and so taking a floor of that basically kills the 1, and it's the same as 2m divided by 2, which is m. Okay, so that's what I will use. If okay, so now we consider this other case, k plus 1 is odd. So at this case, k plus 1 is 2m plus 1, and div, this point in the code, instantiated with n k plus 1. In this part of the code, I will have k plus 1 div 2, which is 2m plus 1 div 2, which is m. Okay, so so that's what my my D will be, right? This m right here. Now, of course, m is again in this range, and so by strong inductive hypothesis, I can assume that FP worked correctly on it. So this value P here is going to be a to the m. And now let's see that because I'm in the n odd case, n is k plus 1, and odd case, I don't care about this cross, but I care about this one. I'm going to return a times p squared. So P is this, which by inductive assumption is correct. So it's a times a to the m squared. So this is again a to the 2m, and it's a times a to the 2m, so it's a to a plus 2m, which is 2m plus 1, which is k plus 1. Okay. Okay. So I have the both cases covered by strong induction, and we had an example of a sequence like this. We had an example of a sequence defined in terms of an element that at index that was half the original index, and it basically gave us logarithmic sequence. If I wanted to prove, you know, here is something that would be also nice to prove quickly. Let's copy this FP algorithm. FP an is if n 0, then return 1. Else compute d, which is n over 2 floor. Then p, which is run FP on this exponent. And then post-process, if n even, then return p square, and if n odd, return a times p square, right? So this is this correction. And I argued before that this algorithm is correct indeed. And now I have a new claim, which is that for all a, f and n greater or equal to 0, fp on an makes at most floor of logarithm base 2 n moles. And actually, this is probably incorrect, sorry. So I'm going to give myself 2 times this logarithm. Okay. I will.
Is that a 12 or 2? I can't really see from here. Sorry, it's is that number 12 or 2?
Oh, 2.
Oh, okay. Thanks.
Yes. Okay. So compare to the previous power an algorithm took n moles. So if n is 2 to the 20, right, which is about 1 million, then this power algorithm used 1 million moles, and FastPower used at most 2 times the logarithm, which is 20, which is 40, right? And obviously, there's a huge gap between these two, right? So you see how much more efficient this guy is, right? And that you would never really want to use the stupid algorithm, this one. You would use this one. Okay, so now, okay, so base case, well, like FP of A0 uses 0 moles, and that's at least 2 times log to 0. Log to 0 is, there's no such thing actually. There is no log to 0. So you know what? I have to modify this for non-negative, non-zero powers. So my first case is going to be n equal 1, and if n equal 1, then how many moles I used? Well, I computed d, which is half of n, half of 1, which is 0. And I computed this, which does not do anything, it just returns 1 immediately. And I'm in the odd case, so I square 1 and I multiply. Squaring 1, even if I count this as a mole, it uses 2 modes. Okay, and this is indeed bounded by 2 times whatever log. Okay, so this is not exactly correct either. So let me change. I have to add 1. Because this is a 0, right? And this is a 1. Okay. Inductive case, right? If you know, I will simplify my work, and so that not to torture you with this ad hoc proof too much, and making sure that these border conditions all work out. Let's do it just for n even. Okay. So if n even case, fp at n used the number of moles equal to, first of all, the number of moles used in the FPA n/2 call, right? But this is simply n/2. And secondly, in this case, right, it used 1 more, plus 1 more for the p-square computation, right? Now, by strong inductive hypotheses, this number, call it A. A is at most 2 times the ceiling of logarithm 2 of n/2. And now plus 1, I guess. Okay, hopefully this will work. Now this logarithm is basically bounded by logarithm 2n minus 1. So this whole thing is bounded by logarithm, and here I have plus 1, so these two cancel, so it's log 2n. And so A is smaller or equal to 2 log 2n. So the whole number is A plus 1, which is smaller or equal to 2 log 2n plus 1 more. So it's bounded by 2 log 2n. Yeah, I don't have, sorry, I don't, wait, what? 2 plus 1/2. Okay, that's good. And this is probably, yes, so this is bounded by this thing. Okay, so, oh. So, you know, simply speaking, you perform at most 2 modes every time you slash the argument by 2. And how many times do you slash an argument by 2 until you reach the base case, right? And you're taking floor every time. So you are slashing it by 2 and a little bit. if the argument is odd. You're gonna do it as many times at most as the logarithm from 2 to the n, right? So this is the number of recursive calls that you will ever encounter, and this is the number of modes that you will at most perform for every recursive step, right? So, and the rest is these border conditions, which I hope I got correctly here for this case. But that was the main point. Okay, let me switch back to the switch back to the to the PowerPoint. Okay, I have some other examples of recursive algorithms. So I want to compute this funny expression. Okay, I want to compute a to the power 3 to n plus 1. I could compute it at least 2 ways. First of all, I could run the exponentiation algorithm on this to compute this first, right? And then I could compute the another power algorithm to compute this, right? Where my argument now will be whatever this gave. This will be an integer because we will have an integer base. So the FastPower algorithm would work. The problem is that well, I could do it. So this would take a logarithm of n steps. But this thing is going to be exponentially larger than n, right? So if the number of steps I will need here is the logarithm of this thing, which is basically n plus 1 itself, well, maybe I'm not going to save much time by doing it directly, but at least it will be simpler conceptually. Let's, okay, the simplicity is in the eye of the beholder, but okay, it's an alternative solution. Let's do it by a direct recursive algorithm without computing this separately and then running another FastPower algorithm on the result. So I want to compute this value, first of all, in some base case. Well, so if this is supposed to work, n is any non-negative integer. So what's my base case? Well, n equals 0, right? And then, well, can I compute this by hand for n equals 0? This is 1, so this is 3 to the 1, so it's just 3. Well, I have to compute a to the 3. Okay, so I computed by hand. I just do a times a times a. That's what I return here, right? And now the recursive case, if I can compute this superpower at one less integer, how would I compute this? So here's my base case, right? And what about the recursive case? So I so imagine that this call computed this formula correctly. So it computed a to the 3 to the n. How would I compute a to the 3 to the n plus 1 given a to the 3 to the n? Again, the chat. So somebody said, okay, why don't you think a little bit, maybe do it on a piece of paper. Try to derive this. So Again, the recursive call P is a to the 3 to the n. Okay, so you think, yes, let's, well, no, this is the proper answer. Okay, so let's look at the derivation together. So by inductive hypothesis, the recursive call gave you the correct value. And how do I get this from here? Well, I can represent this as 3 to the 3n times 3, right? Because 3 to the n plus 1 is 3 to the n times 3 to the 1. I sum up these exponents here. And now this is, I can take the 3 out and represent it in this way, right? Because it's a sequential operations of exponentiation. It's a to the 3 to the n, and the result exponentiated to the 3. So that's p cubed. Okay, so you know, this is the recursive formula that relates the two. So this defines really an exponential series, right? So you know, we didn't think of such a series before. So we defined the nth element. What is our arithmetic series? It's the n minus first plus something. Geometric series is nth element is the n minus 1th times some fixed value. While here, it's the n minus 1 element in the series multiplied by itself, and moreover, twice, right? So it's this previous element to the third power. So you basically, whereas the closed formula for geometric series was an exponential, the closed formula for this series is going to be a super exponential. The 3 is the fact that you are cubing is reflected in here, and the fact that you started with well, with the, so the initial conditions for this sequence, right, is a cube, or it's really 1 if you want. You know, it could be 1 for, I mean, it's really, okay, it would be more natural to define it as, right? I start at 1, at which point this will be just simply a to the 3 to the n. And a is reflected in the fact that no, sorry, I take it back, right? So basically, if I start at 1, then cubing or taking any powers will not get me anywhere, right? I will just continue getting 1s. So I have to start with some non-1 value. And the reason I started with this one is that these two work nicely into this, right? But if you can start it at any point and see what happens, what you get here as a result, right? Derives this expression. You can ask yourself, okay, well, you know, it's by the way, this algorithm, right, is like what I, not a very nice turn of phrase, but I call it a stupid algorithm, right? Like for power, it went linearly, right? This guy also computes this in a time that is linear in n. And if I use FastPower, I don't gain really speed, because this, if I use FastPower to compute this exponent, I would do so using logarithmic in n number of modes. But this value is going to be an exponent of the logarithm. So this would be, if I, so, but if I run FP, this as a base and this as an exponent, then the exponent is 2 to the n, or any power to the n, right? Or any base to the n. So logarithm of this will be n. So even FastPower is not going to help me. Well, so you can ask, is there a fast algorithm to compute super exponentials in a time that is better than linear? the last examples I have was the recursive algorithm for the power set, which is on the homework. So, you know, in case I can just go over this algorithm, right? It's the recursive algorithm to create a power set. And the base case, well, you know, what is the smallest set? Okay, an empty set. And a power set of an empty set is a set that contains an empty set, right? That this is the only subset of an empty set, which is itself. Now, recursively, if I had an algorithm that that can work on sets of smaller cardinality, then I could compute the power set of some set A, okay, as my input, as follows. Pick any element in the set, isolate it, set it aside, and consider a reduced set, which is all the previous ones, but with this one isolated, kicked out. And now, really, cardinality of this reduced set is one smaller than the cardinality of A. So if the power set algorithm worked correctly on sets with reduced cardinality, then this would give you the correct power set of this set. In other words, this would return to you all subsets of A prime. And now think, is there a way to express all subsets of A in terms of all subsets of A prime? And there is, okay, because look, there's two types of subsets of A. First type is they include this little guy who is isolated, and the second, they don't. Let's consider those that don't first. If I'm looking at subsets of A that don't have a little guy, well, these are exactly the subsets of A prime. So if this thing returned to me all the subsets of A prime, I already have essentially half the subsets of A, namely all subsets that do not include this little guy I isolated. So the only remaining case is all subsets of A that include the little guy. Well, but I can represent them in a following simple way. A subset of A that includes the little guy, it's the little guy added to some subsets of A prime. Yes? If A prime is just like A with the little guy removed, then any subset of A that includes the little guy is one-to-one relation with some subsets of A prime. So that's what I'm doing here. I'm basically, my return is this set, which was all the subsets of the reduced set. But now I have to add to it all those subsets of A that did include the little guy. And I'm doing this here. Namely, I'm taking any subsets of A prime, which is returned, which P contains all subsets of A prime by the inductive hypothesis. So I'm taking any subsets, all of them, right, one by one, and I'm incrementing each of these subsets by this little guy that I put aside. This adding is going to create all these remaining subsets, namely the subsets of case one, the subsets of A that did include the little guy. And now it's complete. Okay, and the homework asks you, okay, so this is an intuitive reason, like why would this algorithm work? And do it formally by induction. Just like, you know, throughout today, I was always saying, okay, here is why this algorithm works. Intuitively, this should work. And and just like, and then we phrase it in terms of formal, you know, as a formal argument. You too, you can first trace it on a piece of paper, do a bunch of recursive calls, take a simple set like A equal, you know, it includes like 1, 2, 3, 4, okay, and try to see how this algorithm will actually do through a series of recursive calls. It's more complex than, in fact, any algorithm before, right? So it was like a kind of, I mean, that's the beauty of recursive algorithms. They are very concise. but they actually have great power. And on a very small real estate, you convey a lot of interesting things, right? It's not obvious to see how they work and if they work, do they work, why they work, etc. So write it out and then form some hypotheses about like how would you argue that not only the algorithm works correctly on a small case of some small set that you have seen, but it works correctly on general. And what is the inductive parameter? What is the predicate that you should use to argue this inductively, right? But perhaps you can see it in these informal arguments that I must have used some assumption about the correctness of this recursive call to argue correctness of this code in servicing the upper layer call. And what was the nature of this recursion? Can I cast it as, okay, there is some parameter here and it's an integer parameter and this is the parameter on which my recursion goes. So I'm open for questions. Somebody asks, how would A be included in the power set of A prime? No, so little guy is not included in the power set of A prime. A primes are precisely, a power set of A prime precisely includes all the subsets that do not include the little guy. And that's why I have two cases of the subsets of A, those that include little guy and those that don't. And those that don't are in here already. And here in this loop, I'm adding all those lacking ones which do include the little guy. So N and P form partitions of the power set. Yes. If N, capital N, is all those that were added here, then yes, exactly. That's how you can think of this. Any other questions? Sure, somebody says it's like a corrective measure. Yes, this brings up, yeah, this brings up all the, creates all the subsets that are in the other partition, in the, so somebody on chat wrote that I can divide subsets of A into two sets. Set P of all the subsets that do not include the little guy, and set N, all the subsets that do include the little guy. P is computed directly by the recursive call, and N is computed in here through this loop. These are the, if I just create now N as not add to P, but add to N. And at the end, I return a union of P and N, which is also created here. That would be correct too, and perhaps it's clearer and easier to argue. Can we say that PK is a set and then PK? No, so what, I don't know, somebody says PK as a set, but that's not formal. I mean, I don't know what you mean. Inductive.
Okay, so I can explain a little bit more. So,
and induction goes for integers, right? So induction is some predicate that holds for integers. So find some integer here.
Okay, so because what I can explain a little bit more, because what I said, because not just PFK was just, so I said K was just a set, like just a set or a set of sets of integers, and then because what this algorithm looks like it was doing from the homework, it would look like it was flattening the set to make sure that you had like all just returns a set of all integers. That's what it was. That's what the algorithm was in the homework. So then based off that is like I use strong induction to show that for.
No, you know what, Omar, let's talk offline. So I can have a quick chat with you just after this. But basically, I don't want people to be sidelined by this because it's not. I mean, first of all, it is exactly the algorithm I gave in the homework. there's no integers here. Like this is works for any sets. It's not sets of
Okay.
integers. I'm just recommending that you do it for some set of integers. So on and on, right? So let's just chat offline. I can do a Zoom with you, okay? In a second, all right? So any other questions? Okay, so guys, thank you so much. And I will switch off the recording.